Hello statistics students, my name is Emigh, and this video starts our discussion on section 7.2, estimating a population mean. Constructing a confidence interval for a mean mu would look very similar to the ones in section 7.1, except instead of p hat and p in the center, we are using x bar and mu. The e is still the margin of error. If the population standard deviation sigma is not known and normal distribution is assumed, or if our sample size lowercase n is greater than 30, then we're going to use a distribution called the student t distribution, which was derived from a group of students. The t values are on the horizontal axis. Mu equals 0. On sigma this time, though, it can be greater than 1. The area under the curve has to be a total of 1. Looking at 3 of them here, the one in yellowish gold, that's the student t distribution with a really small sample size, n equals 3. But we can see that if we change our sample size from 3 to 12, look how the bell becomes a little taller and a little smaller in the tails. As our sample size increases, these curves will reach the standard normal distribution curve that we're used to with z. Couple things to note about the student t distribution is that as n gets larger, the t distribution gets closer to the normal bell-shaped curve. It reflects the greater variability, or the wider distributions, which is expected with small samples. The standard deviation varies with the sample size. We can see one example here, how n went from 3 to 12, how the bell changes. And we're used to z sub alpha over 2. For student t distribution, it would be t sub alpha over 2. That will be our critical t value, separating an area of alpha over 2 in the right tail. The program this time, found in the same place, under stat, but we're going to have a decision to make for this time. So let's walk through this. To construct a confidence interval for a population mean, we first want to check if we're given a summary of the statistics or if we're given the actual data. Let's go with this one first. If we're given a summary of the statistics, for example, they tell us the sample mean is this, the sample standard deviation is this, the sample size is this. That's a summary of the statistics, rather than just a list of the entire set of data. All right, so in this case, we're going to go to StatCrunch in that stat drop-down menu, and this is the decision part. They're not going to tell you which one you have to choose. You have to figure it out. And the way you decide is based on, right here, sigma, the population standard deviation. If sigma is unknown, we're going to use t-stats. If sigma is known, we're going to use z-stats. From there, we'll open the one sample menu. We'll select with summary. We'll enter the sample mean that they ask for. We'll tell the program the sample standard deviation and the sample size. We'll select our confidence interval for mu, and then we'll enter the confidence level as a decimal, just like in the last section, and hit compute. Now, if we're given a list of the data, you guys are used to this. You click the little blue rectangular icon located at the top right of your data, open in StatCrunch, stat drop-down menu, and you still have to make that decision. You have to figure out if it's z or t, and that is based on the knowledge of sigma. If sigma is unknown, we're thinking t. If sigma is known, we're thinking z. Okay. And from there we'd go one sample with data this time. Select the column in which your data is entered. Select confidence interval for mu and enter the confidence level as a decimal, followed by compute. Let's see what that would look like. A common claim is that garlic lowers cholesterol levels. A sample of 40 subjects were treated with doses of raw garlic, and their cholesterol levels were measured before and after. The changes in their levels of LDL cholesterol have a mean of 0.4, a standard deviation of 21. Construct a 95% confidence interval estimate of the mean net change in LDL cholesterol, round to 2 decimal places. All right, so our task is to construct a 95% confidence interval estimate of a mean. So we'll have to open StatCrunch and decide if we're going to run a program based on the data or a summary of the data. And it's obvious we don't have the data. There's no table for us to upload into StatCrunch. What we do have, though, is a summary of the data. We've got a sample of 40. We've got a mean from that sample, change in cholesterol of 0.4. We've got a standard deviation from that sample, lowercase s. So we're going to choose the program with summary. Second choice we have to make is whether or not we're going Z or T distribution. Remember, that's all based on sigma. So looking at this information, were we given the population standard deviation? Tempting to think, well, we were given standard deviation right here, but that's the sample standard deviation. The population standard deviation, sigma, this is unknown. Okay, so we're going to move forward with that information. Check out our sample size here. It's greater than 30. Let me note that just so we... All right, let's see what this would look like in... Okay, here in StatCrunch, we're going to go to the Stat drop-down menu and time to make a decision. So we did not know any information about the population standard deviation sigma, so we choose T-stat. This is one sample, and we were given a summary of the data. The mean was 0.4 change in cholesterol level. The sample standard deviation was 21.0, and we had 40 people in this study. We're going to, using this input screen, we're going to ask the program to perform not a hypothesis test, that's for Chapter 8, a confidence interval for mu, and I believe it was the default, 0.95. We hit compute. And here we have lower limit, negative 6.3161258, upper limit 7.1161258. Let's put that in our notes. All right, in our notes, we're going to want to write down that we checked that the requirements were satisfied. That was sigma was unknown right here. However, we had n greater than 30. Those were the requirements to use the student t distribution, which we ran, and accurate to 2 decimals. We got negative 6.32 and 6.12 for our lower and upper limits. We're now asked, what does the confidence interval, CI, suggest about the effectiveness of garlic in reducing LDL cholesterol? Well, if I'm looking at this interval here, we've got negative over here, we've got positive on the upper end, which means 0 is in this interval. 0 is the only number that represents no change. So we're saying here, the way we would interpret this interval is we are 95% confident that the true population mean is between negative 6.32 and 7.20. So it could very well be 7.12. So 0 is between. It could very well be 0. So here we go. First thing was that interpretation. Second, we say the confidence interval limits contain the value of 0, suggesting that mu may be 0 itself. 0 represents no mean change in cholesterol level. So it does not appear that the garlic treatment is effective in lowering LDL cholesterol. All right, let's try another one. In recent decades, the mean weight of men has increased considerably. We need to update our estimate of that mean so that boats, aircrafts, elevators, and other such devices do not become dangerously overloaded. Using the weights of men from a random sample, we obtain these sample statistics. So we've got 40 again. We have a mean weight from that sample of 172.55. And check this out. We have sigma. So it's not the standard deviation from that sample. That's the population standard deviation we're given there. Okay. Part A wants us to find the best point estimate of the mean weight of the population of all men. I like to think of that as the best guess. And it's actually provided to us right here. This is the best guess. It's always the sample mean. Part B wants us to construct a 95% confidence interval estimate of the mean weight of all men to 2 decimals. Okay, so remember, we're going to be, once we open StatCrunch, we're going to be faced with that decision, Z or T. We are given, we know the population standard deviation. So that right there, that means that we're going to use Z, standard normal distribution. All right, let's see what that will look like in StatCrunch. Okay, we'll go to that stat drop-down menu. Our decision is Z distribution this time. 1 sample with summary. The sample mean was 172.55. The standard deviation, notice it doesn't say sample standard deviation, it says standard deviation. So the population was 26 pounds. Sample size was 40. Confidence interval with the default and compute. Lower limit 164.49266, upper 180.6734. Let's see what that will look like in our notes. Okay, for part B, we would write that interval up as accurate to 2 decimals, 164.49 is less than mu is less than 180.61. Part C says, what do the results suggest about the mean weight of 166.3 pounds that was used to determine the safe passenger capacity of water vessels in 1960? Okay, so we look at our interval and we're checking to see if 166.3 is in here. And 166.3 is between the lower and the upper limits. So it is with 95% confidence that we believe the true population mean could be in this interval, which contains 166.3. However, this new mean weight that we found, 172.66, is 6 pounds more than what it was in 1960 based on this sample of 40. And because this situation could potentially involve fatalities, it's about people's safety, we wouldn't want to just go back with the 166s in this interval, so we go ahead and use the old 166.3. We would want to say something like the mean weight of 166.3 pounds used in 1960 could be the mean weight of men today. However, the best point estimate of 172.55 and the upper limit of 180.61 pounds suggests that it could be considerably greater, and therefore more data values should be collected. If we're asked, what's the minimum sample size required for estimating a population mean, then we're going to use this formula here. You guys have already written down 2 sample size formulas in the last section. They both started with n equals. So this is our third formula for sample size. See, it also starts out with n equals. So I would suggest you write all 3 n equals formulas onto your reference sheet so you can use it during any closed assessments. This one right here would be used for population means. This table is the same one we were referring to before. So if our confidence level is the default of 95, then our z sub alpha over 2 is that 1.96. No change there. Let's try one. Assume that we want to estimate the mean IQ score for the population of statistics students, in which sigma is 15. Must be IQ score points. How many statistics students must be randomly selected for an IQ test if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? All right, so they have, let's check if they provided us with everything we need to use this n equals formula. They asked us how many, so we got to go n equals. And instead of the z sub alpha over 2, that variable, we're going to replace it with 95% confidence, so 1.96. Okay, so here this will become a 1.96. Let's see if they give us sigma. They did. It's 15. And the last thing we need to use this formula would be the margin of error, capital E. It is written in words here, so got to read it carefully. It says 95% confident that the sample mean is within 3 IQ points. So this is going to change to a 3. Okay, we definitely have everything we need. Plugging it in to the formula, we'd get a 1.96, a 15, and a 3 in those blanks, which leads us to 96.04. And we know that with sample size, we would say with a simple random sample of, and we always round up, 97 statistics students, we will be 95% confident that the sample mean is within 3 IQ points of the true population mean. Section 7.3 is on estimating a population standard deviation or variance. And we can see those confidence intervals written as inequalities. Notice that we are using lowercase s and sigma. Lowercase s is for the sample standard deviation and sigma is for the population standard deviation. And if we are constructing a confidence interval for sigma squared, that would be for the variance. So we have to have s squared for our sample variance and sigma squared for our population variance. Capital E is still the margin of error. When constructing or working with standard deviations and variances, all of those values are positive. So notice that if you graphed them, see this graph here? Notice it's all quadrant 1. And that should make sense to us because if all of the standard deviations and variances are positive, they're all going to get plotted and graphed in the first quadrant. So this distribution, this shape that you guys see right here in quadrant 1, this is called the chi-square distribution. The sample statistic chi-square, this is the Greek letter right here, chi-square, has a distribution called chi-square distribution. All right, you can see that it's not symmetric like the bell-shaped curve. There's this longer tail here. All values are non-negative. And here is a nice visual on how that graph shifts based on DF. DF stands for the degree of freedom. So it's typically 1 less than the sample size. So if you sample 11, then your DF or degree of freedom is 10, and the distribution is going to look something like the blue one. If your sample size increases, let's say you're at lowercase n equals 21, then your degree of freedom is 1 less than that, which would be 20, and your distribution will look more like the red one. So it adjusts based on the degree of freedom. Just writing those down. 1, it is not symmetric, but as the degree of freedom, df, which is equivalent to n minus 1, increases, the distribution becomes more symmetric and approaches a normal distribution. The values of chi-square can be 0 or positive, but not negative. And the critical values of chi-square are dependent on the degree of freedom, which is again n-1, and can be found using the chi-square distribution table. There's a link to it in StatCrunch right in the exercise in which it's needed. Okay, speaking of StatCrunch, confidence intervals for standard deviation, sigma, or variance, sigma squared. 2 possibilities, just like last section. If you were given a summary of the statistics versus if you're given the data. Once you get that loaded up in StatCrunch, you can see here the program we're going to use is called variance stats. Variance stats. And it'll be the one sample menu with summary, should that be what you have, with data, if that's what you have. And then on the input screen, you're going to need to tell the program the sample variance, the sample size, and select confidence interval, and tell the program the confidence level as a decimal and compute. Or if you're working with the data, then you just select the column in which the data is entered, confidence interval for sigma, and then the confidence level and compute. Let's try one. A group of 22 subjects took an IQ test. The subjects had a standard deviation IQ score of 14.29263. To the nearest tenth, construct a 95% confidence interval estimate of sigma, the standard deviation of the population from which the sample was obtained. Let's see what that looks like in StatCrunch. Okay, so we go to our stat menu, and program is variance stats, one sample, and we were not given the data, we were given a summary. The sample variance, okay, this is interesting. They didn't give us the sample variance, they gave us the sample standard deviation, 14.29263. No problem. If given the standard deviation and the program needs the variance, we can just use any calculator, and we need to square the 14.29263. So take out a calculator, 14.29263 squared gives us our variance of 204.279. I'll go with 3, round it off there. Okay, sample size was 22 subjects. And we're not performing a hypothesis test. That will be chapter 8. So we want to click on confidence interval for sigma. 95% is the default. And we hit compute. Okay, here we have our output screen. DF is 21, one less than the sample size of 22. This 10.282898, that's called the lower critical value. So it's chi-squared capital L. And this one is the upper critical value. So it's like chi-squared capital U. It's 35.478876. Here we have the lower limit and the upper limit. Okay, let's see what we put in our notes for this. Oh, first I want to check this. Okay, it just gives us the confidence interval. I was curious if it would give us the... All right, so we will look at that distribution graph ourselves right here. There's that 10.283. There's that 35.479. This is the alpha divided by 2. That came from the confidence interval was 95%. So sigma is the other, so alpha is the other 5%, and you have to divide it by 2 to get half of it in this tail and half of it in this tail. Our confidence interval, there's the 120.9 and the 417.2. Now this is the confidence interval for the variance. You see it right here, sigma squared makes it variance, but they've requested it for standard deviation. No problem at all. Just take your calculator back out and do the square root of each of those limits, and we will get our confidence interval for the standard deviation. So we are 95% confident that the limits of 11.0 and 20.4 contain the true value of sigma. Okay, my name is Jamie Emigh. That will finish our discussion on chapter 6 and 7. I will see you next time.